So our next presentation is about CAP class for big data. And welcome Justin C. from Temple University.
Thank you. I think you're still waiting, right? You have a nice pizza and good lunch. I figured that I think a keynote speaker already set the stage for my talk, so I guess you're prepared. And I was, because I have a sweet talk today, so I'm going to keep you here for a while. And I'm going to start one that's a little simpler, and it's probably easier to get started. And because Mooney mentioned a few keywords that actually set the stage for my talk. Well, I want to start with a little joke I borrowed from my friend. Is that when NASA's Mars rover landed on the Mars successfully, and it was hailed as a scientific discovery, success. When Mars rover crashed, did not land on Mars successfully, you know what it's called? It's called engineering failure. Okay, now, it may sound strange, it may sound unfair, but it's really bloody true. For those of you who actually do engineering, and we're in a really difficult business, because our failure is the easiest to see. A scientific discovery is very hard to prove or disprove, but engineering failure is very easy to see. So here is basically the topic of my talk. I'm going to start with this, and I'm going to challenge your common senses. And I'm going to take Ms. Mooney's talk a little step forward, because it mentioned a keyword called eventual consistency, which happened to be CAP theorem. So really, that's my little sweet talk. I pushed that CAP plus is probably the hardest problem that to be solved, so I pushed it again. So with the permission, I'll proceed. Would that be okay? Thank you. So I just came back from a meeting at the National Science Foundation for reproducibility. I don't know how many of you have heard such a thing called the reproducibility problem. Probably not. You see, it's kind of weird, right? Software is always reproducible. If you write a program, how can a program not be reproducible? Does that make sense to you? Apparently, the problem doesn't exist. The question is why? Why a program become not reproducible? Why even there's such a problem? So actually, it's a national level. So I'm going to start with this overview slide. So I will list out the fundamental big data challenges, because I think my talk is the only talk that deals with infrastructure, which I think Moody and I share some kind of interest. And the top level of the policy challenges, and we need to decide what to collect, we need to decide what to store, we need to decide what to analyze, and we need to decide what to share. These are the policy issues. I have nothing to do with beyond my pay grade. Okay, I'm not interested. Then there's the implementation challenges, and we decide how to collect data. And then we decide how to analyze data in extreme scale. Now because why have to do extreme scale instead of small scale? Since Moody's 6,000 machine actually makes a lot of sense to me, because without that scale, you cannot reveal the problem. I will go one step further. I probably need a 60,000 machine test to prove a point. And they have to study how to store the data, and the data can go indefinitely. And then you want the processing time to keep it constant. And how can anybody do that? If you don't do this, and big data just go empty talk. Because the data is growing every day. And use your cell phone, all the logs are saved. Storage is really cheap today. Is that right? So do we or do we not have the capability to process the data? Do we or do we not have the intellectual understanding what the software engineer really is about? And how can we launch a supercomputer that will never fail? So these are the challenges that we have to face. So my talk is actually this particular talk. Is this one. It's called reproducibility. And the last one I will share, the red ones are the one that I will address today. The three talks, my three talks are in this around these three areas. This talk is reproducibility, and there's one called modeling. Okay, modeling means that You see, in computer science, we have something called garbage in, garbage out, right? So the web data is really considered garbage in. Okay, but we can always produce garbage out. And usually we don't share the model we produce, and you see, we really cannot rest on one because Google said this is a bad guy. Or can we? So there is a big difference between the big data and what do you want to do with the big data. There's a huge amount of work in there. So I'm going to address this as red points, and the rest will leave for you guys to play. Now I'm going to defend why we have to do extreme scale research. Okay? If the scale of research and analysis is small, you really can see the problem. You see, everything works. Any model works in small scales. Okay? If you blow up the scale into bigger, larger scale, extreme scale, and examine things, and the problem will explode themselves. So this is why we have to do extreme scale research, especially for software engineering. Because software engineering is not computer science. Is that right? So how many people here know the difference between a scientist and an engineer? Hello? What's the difference between a scientist and an engineer? Hello? Yes?
Engineer applies the findings of a scientist.
That's right. Engineer apply findings. So what is it is applying, and I will say characteristic-wise, a scientist is very reluctant to compromise, and usually they don't. And an engineer have to compromise every single day. And in the process, engineers are more likely to make mistakes that are visible than a scientist. So engineer's job is much harder. So without understanding science, engineers are more likely to make mistakes. Is that right? So this is where I'm coming after. I'm after the fundamentals. The fundamentals of building a large system that will last forever and will not die. And the fault tolerance is not a separate issue, but it's an integral design issue. It's a part of architecture. Now, I don't know if you guys have read the 2012, there's a community-wide paper by a bunch of people from Stanford University called the 21st Computer Architecture. How many people have read that paper? Very few. Okay? So that paper particularly said there's an inflection point currently in industry and in academia. So computer hardware, software, all the developments point to a point that's going to dip down. Moore's law is going to stop. So all the speed calculation no longer works. Then we talk about the big data keep growing. So the trajectory is the data is going this way, our machine power is going this way. There's an inflection point. If we keep the way we're doing a business, something bad is going to happen. The train already dropped the hill. You see what I'm saying? So this is where I come from. So the reproducibility challenge came from the 2009 at the Yale University. There was a roundtable discussion in the law school about a biology professor published a paper. It got nationally funded, vetted by National Science Foundation and the National Institute of Health. And it was a biology discovery after a supercomputer calculation. It was presumably solve many long-term genetic disease problems. And the clinical trials, all the funding was in place. 3 months later, it was recalled. Why? It was a calculation mistake. Well, people got alerted. Because there are big consequences, a lot of money spent. Who's liable? Would the scientists lie in? Maybe not. And then why this very well-known research is not vetted within the own community? Well, there's an honest mistake. So it turns out, among 67 nationally funded research, only 17 can be independently reproduced. So that becomes an epidemic. So why a software produced, it cannot be reproduced? And this is what we found. We kind of spent one day in Atlanta, and a bunch of people there. They're all supercomputing people, and they're all doing numerical calculations for living. So they're breeding MPI for living. And what we found is the dependencies of the big enemies. Now, do you guys know what the dependencies are? What is the dependency? Software dependency. If I want to run Moody software, I have to go to his GitHub, download the software, and his software will depend on 3 other packages, maybe more. Okay? If any of these packages not meet the requirement, then the software isn't going to work. See, it's not that you download Moody's code that's going to run. No, it's not going to be that simple. And moreover, and one of the libraries may depend on a particular piece of hardware that only Google has. Okay? The whole thing will break apart. So don't just think that open source is a great thing. It's not. There's a lot of, let's say, flies in oil kind of bugs in there. And I've been there and I've seen them all. So the problem is how can we, as a community, produce a software that can be reproduced and that the scientific result can be checked and verified before they go to broad adaptation and before they cause more damages, then put that way. So dependencies have made it impossible to gain performance and reliability at the same time if we upscale the processing. So this is what see, we were actually talking at the lunchtime yesterday, and we had a great time. And they challenged the audience and said, I think there are quite a few students here. Let me ask you this. You see, all your teachers tell you, when you have a program, right? You put 10 machines there, it gives you 1 performance. And it gives you 1 reliability. Suppose they give you 11 machines. You get a better performance or better reliability. You can only get 1, is that right? Yes or no? You see, all of you straight mind say, okay, you can either get a better performance or reliability because 11 machines, the likelihood of 11 machine die is bigger than the 10 machine you die. And any of the machine dies, you die. Is that right? Maybe yes, maybe no. Well, see, something wrong in that picture. Something wrong in the engineering principle. The scientific principles are not in place when engineering practice was broad applied. So this is where I'm coming from, okay? So all of you are very used to remote procedure calls, yes? RPCs. You see, Moody mentioned that. It's a remote procedure call. Okay? You know what the remote procedure call is? It's called explicit programming. Okay? It binds a program with another program. Now once you do that, you kind of kill yourself. Because if that program is not there, you die. Right? You have no recourse. You have no place to go. So let me show you why explicit programming is so bad. And we have been cooking this for a long time. We've been drinking off this Kool-Aid for quite some time, about 30 years right now. Okay? Now here is the dependency on the weakest links. You see, all of you have a steady TCP/IP, right? You see, this is a picture of a 7-layer TCP/IP link. Okay, this layer, I think your professor taught you before, in the 7-layer here, everything is hunky-dory. So the professor teaches you that, I teach you how to write a program, and this program, it depends on a virtual circuit. The virtual circuit is auto-preserved, errorless, it's error-free, and a retransmitted, reliable data channel. Is that true? No, it's a lie. You know why it's a lie? Because it is only true from here, from layer 1 to layer 4. You see, at packet level, there's a retransmission. Yes? Anything goes wrong, you're retransmitted. Anything above, you're naked. You have totally not protected at all. Now, to make it matter worse, none of you know how to deal with timeout, do you? You see, no textbook so far today even write about it. Computer science professor dropped the ball. They'll teach you how to deal with timeout. If you're a student, you go back and ask the professor. So here this professor, she's from Temple University, asked me a question. So how do we deal with timeout? I have a buffer. I send it to a computer. I say send. And then what? I wait. If it comes back, you're hunky-dory. If it comes back with success, you're hallelujah, right? It's great. If it comes back with an error, you check the error code, it's okay too. What if it doesn't come back? What do you do? It times out. What do you do? I guarantee you, 99% of people don't know what to do. Okay? Now, if you can imagine the world of a computer built, including Hadoop, including Spark, is fundamentally flawed. Alright, so let me move on. So I dropped down my bomb, right? So I say, hey, how does the reproducibility come through? Because that is the place where instability was introduced from a layer 5 to 7. And then your code, the application code, NPL code, don't even handle timeout. They assume everything going hunky-dory. It's not true. And everybody believes it. No wonder high-performance computer programs cannot run longer than 60 minutes. If the number of processors more than 1,000. So this result came from CMU. Professor Chick with Professor Garth Gibson. Yeah, so he 2007 paper. So he actually did a study on it. So now we're going to connect reproducibility with the scalability. Okay? A scalable program is more reproducible than a non-scalable program. Would you agree with that? Yes. Okay? A non-reproducible program is most likely is not scalable at all. So therefore, scalability is the most necessary and a sufficient condition for reproducibility. The question is, how do we get there? So here is my proposal. Okay, my proposal said you have to do some kind of decoupling. So I was the first one to propose a decoupling. Someone else did before, something like the Linda system also from Yale, called Linda system. But the Linda people did not realize this picture. Let me show you this picture. This is a very interesting picture because I was challenged by students and non-faculty and then co-workers. And I say, how can you prove you can get a performance that we don't have at the same time? You see, in Mooney's mind, that you get performance, you get a high performance, you get a low reliability. So fault tolerance is really challenged. So kind of shy away from the topic, right? But I'm saying that you really can get a performance that we have at the same time, otherwise the architecture is flawed. Follow me? So let's look at this picture. So the top picture is called explicit parallel program. Okay? This is a program, and this is a processor. You bind it. Okay? The program binds the processor. If the processor dies, the program dies. Explicit. Okay? When you scale it, okay? You add the processor, add the job. So you have now two processors can do two jobs, so you get a better performance. But you have a less reliability because any process dies, you die. Is that right? So you cannot scale it. In implicit case, okay, the program is not a hard bind, it's decoupled from processor. That means the same program can run on any processors. Is that right? Okay, this is a critical point, alright? So I have a little circling here. And I scale again. Okay, I have two processors, I have two jobs, I get a better performance. Okay, now what machine die? I don't die yet. Okay, because my programs can run any process, right? Did I say that? Yes, I said that. Okay, I have a magic switching device. So any processor dies, I'm going to switch it to another processor. So this entire application will not die until both of them dead. So this red cross, the red cross should be half of size. Is that right? So if you do that proof mathematically, by induction, what do you get? You get an infinite scalability. You add a processor, you get a better performance and a better reliability at the same time. There's no upper bound. Now this is totally counterintuitive, but it's true. It's so simple. Right? Can you even argue with it? It's really hard to argue with it. So here's my secret sauce. So how can you see computations all over places? You see, people like Mooney have done a lot of key-value pair calculations, okay? But probably you're the first time you hear about tuple switching network. Hello? See, something that is called a tuple switching network is necessary to cover this virtual circuit flaw. You see that? If you can statistically multiplex the tuple switching network, and then you get a performance and the reliability at the same time. Otherwise, you can't get there. So this is actually the picture of something called tuple switching network. So there's a there's a journal paper we published in the Journal of Distributed Parallel Computing in 2012, and it details how that the triple switch network look like. So we apply that, and then you get a better performance at very the same time. So it's really not that hard. It's already done, and I have a code. I'm also on GitHub. You can download it. So the key of this thing is something that is optimizable. See, this is something like optimizable for different. This is something that you never dreamed of about API programs. Is the API programs you partition your job, right? Say, what are you talking about? You take, say, 3,000 feature vectors you want to calculate, and you select, like, say, 1,000 processors, and each processor has 3. So divide it, so n divided by p. Okay? Do you think it's going to come back? They all come back at the same time? 1,000 processors, each get 3 jobs to do, and they will come back at the same time? No, they will not. Okay? Now, if they don't come back, what do? You have nothing to do. You don't know what to do. You're stuck because your binding is hard. So what we can do is to do something called a dynamic binding, so we can change the granularity. Once you change the granularity, all of a sudden your new dimensions open up. So you can get a better performance, even better than explicit parallel programming. Even better than API programming. So here we did some tests. So what is exactly I call this called the statistic multiplexed computing. So I don't know how many seasoned programmers here, okay? And there's someone in the audience saying, hey, I know how to do timeout. I resend it. Okay? Because they have to resend it. How hard is that? Right? Is it timeout? I resend it. Okay? So my argument said, okay, it's great, you know how to resend it. Okay, suppose that last message is send a $5 million from your account to my account. Would you do it again? You only promised to send me $5 million, but you're going to send another one. You don't have enough balance there. So you cannot. Okay? Number 2 is even if you do that, and the resend will only go through the same path as the last message, the improvement is statistically insignificant. You're not going to change anything. Okay? Your gain of the reliability is insignificant. So only if you can guarantee that every resend is going different path, and then you can gain reliability. Is that right? That's why the switching part. Without the switching part, you don't get nothing. So only with the switching part you can get the reliability and the performance at the same time, incrementally. So that's why it's called SMC. So I gave a talk last year at the National Center for Atmospheric Research, and they're all stunned. They say, how do you say that? We've been living and breathing NPI all my life. You know, we have so many PhD students, created, generated, working on this cache coherence, you know, all kind of, you know, eventual consistencies, which are covered in my last talk, which is probably the hardest topic ever. And how do you say that? Because we said we have a left off first principle. The first principle is not, it should not be explicit parallel programming. It should be implicit parallel programming. What's missing is the switching device. We did not know how to do it. So now we have a new dimension of performance optimization that we didn't have. It's called tuning. So decoupling affords me the tuning capability. I can tune the size of the jobs. I can change until I reach an equilibrium of finishing time. Now without that, I can optimize. You see, you saw moving the picture. You see, a lot of waiting time, right? The green bar and the yellow bar. A lot of yellow bar, there's a waiting time. How do you minimize the waiting time? By finding the equilibrium of finishing time. Without that capability, you're free to fix this. If your partition is fixed, you cannot change the partition size, and you can never minimize the yellow bar into 0. If you can do that, and you test, and I guarantee you the yellow bar will come to 0. You only left the blue bar, and the blue bar is shorter than the one you do asynchronously. Mooney, is that right? You see, Mooney actually did an asynchronous computation. What he did was say, suppose I don't wait for it. I'm moving forward with my calculation. But you pay. Because you pay for extra calculation. Your blue bar is higher. Right? Even though you save your communication, it seems that way, you pay for calculation, which is more expensive. this is in business, okay, in this community. How many of you have learned Amdahl's law? Amdahl's law? No? Oh my God. Have you taken computer architecture class? Tsinghua, you don't teach computer architecture class. I can't believe this, okay? You better take one, computer architecture, okay? Learn something called Amdahl's law, okay? We'll teach you how to do scalability analysis and teach you how to calculate the future potential of scalability of your program. Now, once you learn that, you find, well, it's really hard to apply. Because the professor is talking like they're talking both sides of the mouth, you know? It's like, one side it says right, and the other side is wrong, and then I cannot apply. The student is a student. And he kind of dumbfounded and said, I don't know how to apply. You ask the professor, even him had trouble to apply. Because the law is indefinite. Okay, now there's another law called Gustavus law. Okay, two laws kind of side by side. And the Gustavus law is the beginning of a massively parallel processing movement since 1995. See, I'm telling you the truth. I'm a very old guy. Okay? I've been around for a long time. Okay, and this is happened in history, in real life. Unfolding from my eyes. I saw that happen. I lived through all this. Now, once a community is guided or misguided by these faulty principles, what do we get? We get engineering failure. Hello? We get engineering failure. Now, a supercomputer, the top500.org will publish only one number. You know what number they publish? Performance. And how do people get performance? I run 1,000 times, and I only one time hit the performance and publish the results. I did not lie. Am I right, Bully? I'm not lying to you, okay? It's true. Happened. Okay? The other number, reliability. Nobody publishes it. Everybody hides it. Americans, Chinese do the same. Russians not in the picture. I mean, Germans, French, everybody, Koreans are actually pretty big on supercomputing now. Unlimited scalability actually confines you with your consciousness. You say, hey, this guy is not telling me the truth. He cannot have unlimited scalability. I mean, everybody has a limit. Everything has a limit. And how can you even say that to me, you know? But you really cannot find argument against me, and you're kind of wondering about this, right? But let me give the rest for you. Okay, the rest is easy. Okay, something called diminishing of returns. But that is not the law of physics. It's the law of economics. Okay? Given the problem size, and the more resources you put into that, the efficiency you gain by the resources diminishing over time. That's the law of economics. So both laws, actually both rules exist at the same time. You don't believe me? Try yourself. Both must exist. Unlimited scalability and diminishing return exist at the same time. So the practical challenge. You see, you have at this point you say, okay, this guy may be right. Okay, at least I was able to convince an SF guy to give me some, leeway. Right? Say they still don't want to fund me. All my proposals rejected. And but there's a practical challenge. This committee has been invested for the last 29 years, billions of dollars, produced very good results, but there's no future. That's the problem. Okay? And how do we change that? How do we turn the ship around? So I come up with an idea called wrapping. Okay, I have this paradigm, and I say I can give you performance and reliability at the same time. So what if I give you a wrapping of your legacy code and then put on my new paradigm and then see how the difference goes, right? So in Google it's called dog fooding. So it's like I'm creating a new dog food, and with my dog eat my own dog food. So I'm going to feed my dog with my own dog food. My own dog eats it might be good food. Follow me? So I'm going to do that dog fooding test. So here's an idea of I take matrix multiplication, a classical textbook matrix multiplication, parallel, MPI, talk about internet. Okay? I run optimized version on the classical HPC cluster. Okay, 16 processors, and I'll wrap it. Okay? Now 6,000 by 6,000 matrix. Okay, divide by 16 processes, so even every process gets 375 rows to calculate. It's very simple calculation. Okay, so you get a one performance, the straight line, the green line on the right side, the green line, the blue line on the right side is the NPI performance. Okay, and then I do the same code in a wrap version, and then I have a little flexibility. I can optimize, I can tune the values. So I change the values, and you see the numbers are starting up and down. Okay. The low points are about way ahead here, way ahead of NPI. How much? 10%. Okay? Now that tells you my equilibrium has been reached at this point by changing. Now look at the size. This size is way smaller than 375. You see, 375 is over here. This is 375. Okay? This is a very small number. So it tells you how much is left. Mori, take note. This actually talks for you. This talk is for you. Okay? You can talk to your advisor and say, this Professor Shi gives me all the controversial points. And I never heard of it. And I had a little quarrel with Eric Brewer, by the way, and I'll come to the third talk. Okay? The summary is, computational scientific research is a necessary condition. Okay? Reproducibility is a necessary condition for scalability. Okay? It's a necessary condition. A scale application is always better reproducible than non-scale applications. And the scale application must be implicit parallel, not explicit parallel. So RPCs are bad, RMI is bad, and MPI is bad, OpenMP is bad. For large scale. For small scale, yes. For large scale, they must be wrapped. So that's what I said today. It's August 7th of 2014. So we can remember that. Okay? Now, SMPMC, Static Multiplier Computing Application, can be optimized to outperform expert parallel program. I just showed you how to do that. And the scalable application must be reliably, quantitatively predictable. And the legacy application can be re-engineered to make them to behave. Actually, it makes sense because this is like an analogy internet. You know what the internet is about? The internet is a combination of a circuit switch and a packet switch networks. The backbone is circuit switch. The edges are packet switch. But in a computing arena, we have to reverse it. The circuit switching pieces should be inside. The packet switch should be outside. It's a wrapper. So about that, and I'll close my talk. And this research is supported in part by National Science Foundation and multiple National Science Funding travel grants and industry sponsors, T.J. Watson, IBM T.J. Watson Research Center, and Digital Equipment Corporation, and investors of a Parallel Computer Technology Inc., which is my company, and Mr. Chris Galley, who's my former student, who funded this very trip. So I'm going to save for questions. Questions, guys? Any questions? I dropped a bomb. You should have some questions for me. Yes?
Yeah, thanks, Professor Xie. It's a very interesting talk. So, actually, it's not a question, maybe a comment. Yeah. So, for many machine learning problems or many machine learning applications, most results are not reproducible. So,
now, those are called, I see there are two kinds of applications. Okay, the one application, one kind of a computer programs. Okay, let's talk about computer programs. Two kinds of computer programs. One kind of computer program called deterministic computer programs. So given the same input, always produce the same output. If the input don't change, the output is always the same. Okay? The second kind is the input don't change. The dynamic factor in the program, the output is always be different, which is the one that you're talking about. The non-deterministic algorithms. Okay? Now, as far as an application is concerned, application actually accept the different results of each time run. You see that?
Yeah.
So the application, from application viewpoint, and the person who run the program accepts every time it should produce different results. It should. So either way, it's acceptable, semantically acceptable. So that's where the key is. Okay, so there are actually four. If you dive in, there are four different we call it stability types. So you have a non-deterministic input, deterministic input, not just output, deterministic output. So you have a four quadrant, and you find that your program fits into any of these four quadrants. And then actually it goes further. Actually, I say your argument goes further. There's one step that I didn't have time to talk about is how do you do fault tolerance? You know, I have a master program, and I have to distribute all the jobs in there, and then you have how do I protect my master? These are the more details, but I can go over with you if you're interested. So I can do zero checkpoint. This is like, how do you do zero checkpoint? You know, I have a massive panel process. You have no checkpoint. How can you do that? So this is my talk with NCR. NCAR, the National Center for Ethnic Research, because their checkpoint takes a long time. Each checkpoint takes 3 hours of time. Now it's taking 5 minutes if they write much smaller fonts. But you know how much electricity they're paying for? It's a lot of electricity bill for 3 hours of running. So it's very expensive. Okay, checkpoint is very wasteful. You just don't want it. Don't want to do it. Okay, let's see. Okay, here's another. Okay, so I'm going to move on to my next talk. And next talk, actually, to remind you, my next talk is modeling. Modeling. The next talk is the modeling in the. This is a story. Let me start the slides. This story came from a city. I came from a city, Philadelphia. I don't know how many people have you been to Philadelphia before. See, I think Arthur has been there. Philadelphia is the oldest city in the United States. It's a funding city, like in China, it's the equivalent like Tsinghua的延安. It's almost like Yan'an. Okay, but Washington D.C. is like Beijing, right? But Philadelphia is like Yan'an. Okay, and it has the old Constitution Center and all this. The city has 1.5 million residents, but it has 50 million human health data. Now this is funny. Okay, this is the problem that I was called in to solve. And they say, hey, Dr. Shi, you're expert in parallel processing. So we're into a speed problem. They presented to me as like a performance issue. Our database is running so slow. So can you help us to make it faster? Can you make it parallel? Make it faster. So okay, let me take a look at it, right? It turns out it's not a problem of speed at all. It's a problem of a computer science that we want to solve. All right, now in China, everybody has a car, right? You have a 身份证, okay? In US, we don't have it, okay? And the city of Philadelphia, the public health department has 11 agencies. Okay, that includes prison, mental hospital, and what's called homeless shelter, and some juvenile delinquency programs, and the drunk driving, and teenage pregnancy. All that kind of 11 agencies that handle different issues, okay, human service issues. So all these agencies have their own databases. Some Oracle, most of Oracle, some are Microsoft SQL Server, some MySQL. They have their own data sets. They have their own collection methods. But the city government need to consolidate all the records into a single database. They call the human service database. Now, how do you find, say, Moody's gone, in a database? Suppose that he lives in Philadelphia. Suppose finally the name Justin could be spelled 5 different ways in a lot of databases. Okay? Now, this is the problem that computer science don't have a solution. So the challenge is to consolidate multiple structured databases. They're all structured. They're not even semi-structured. They're all structured. Okay? Relational databases. But we cannot rely on unique identifier. The social security number, even they're there, 60% of records have no social security number. And 40% do have a social security number. There are typos and missing digits and the transpose digits. So they're just not reliable. The question is what to do. So current state, I don't know how many of you have done, how many people have worked in industry? Only Moody have worked in industry. Okay? Industry is something called a data warehouse. Okay? In data warehouse business, there's something called a data cleansing. Have you seen data cleansing program? This is like a weird stuff. Maybe some people don't talk about this, you see. And the professors don't teach this in the classrooms. Okay, but I think they should. They should. So data cleansing means that everybody type in an address and a name in their own way of shorthands. Okay, like the street is ST. Okay, and sometimes STR. Right, and with period. So data cleansing means we'll force all these patterns into the standard form. So the idea is to force all the data into a single relational database model. You know how hard that is? It takes a long time to make things happen. Now in the process, what happens, they overwrite data evidence. The raw data evidence is lost in the process. You can no longer, once that happens, you can no longer trace back what has happened in history. Well, so what we have done is that we did, this is my old name, okay, and so what we did, so this is not my thought, this is my student, okay, he just cannot be here, I don't have money to pay him here, so since I was here, I presented for him. I directed study, so I put the stuff into work, so we came up with something called a probabilistic signature hash, okay, so what we do is, I do quickly this one. This actually is an interesting story. How many people remember there's a mass code processor? Mass code processor. You don't remember? It's like a 386 era. Okay, you buy a processor 386, and the vendor will tell you, say, okay, I'll sell you a mass code processor to make a mathematical calculation faster. Okay, and you don't see that anymore. But at old time there is this thing. Okay? Now, identity matching, this very particular problem, does not fit into a main processor. It needs a special processor. It needs a co-processor, in addition to the engine that Moody and others are building. So what we did, you see, this is a little statistics, okay? This is how what he told you that. And the police will come to our database looking for evidence. Say, can I find XYZ and a particular address with a phone number, and then find me all the match records. And the current database, the match rate is 60%. So this is what happens. So they will do data cleansing, 100 Market Street into 100 Market Street. Okay? They want to see that. There's an ETL called extraction, translation, and loading to fit a single relational database model. And the processing time, I think I'm allowed to disclose the time, is 6 hours a day before the data can be used. Every day. It takes 6 hours to process 11 inches of data, put it in the database before the database can be up for query. Okay? And the time is growing. And the matching rate is less than 60%. 40% is mismatch. So police just cannot arrest the guy. So I have a record, but I cannot be sure this is the guy you're looking for. So do more work, go back. So this is the current state. Okay, the fundamental problem, this is the fundamental. Exact matching is unlikely in this case. You're not going to find exact match. So what does it mean for approximation match? You see, and Moody has mentioned the similarity vector. So what do you mean by two strings? So all the data recorded in the computer are most of the typed by hand, right? All the data that we collected, big data or small data, are collected by fingertip. Okay? And why is not string matching not used for identity resolution? So we are curious about that. Data warehousing systems do not use string matching. It's kind of weird because the complexity is too high. It's n squared complexity. You have millions of names, a short string to compare. It takes forever to finish a matching searching million entries. The second is because exact match is unlikely, all the power of a relational database goes for nothing. No power. You cannot do index anymore. How do you search anything? So all that goes to that. So we are actually in the beginning of building a new system from scratch. So this actually has, I think, a lot of people interested, all right? Particularly government agencies, they want to sell, cannot give me this. So what we did is we did an edit distance. Okay, we define approximation matching by a single number called k. Okay, you define, as you as a user, you define if two strings are considered matched, if the kth number, after permutation, transposition, whatever the manipulation, after k positions, the two become the same, you consider the two are the same. If a k transposition does not translate to one string transformed to the other, you consider these are absolutely not to be same. So there's something called a k safe. You can prove mathematically that if k safe, you meet that criteria, and then you're going to miss anything. Okay? Once you have that defined, you create a multi-dimensional identity vector with a graph matching engine, and then you iterate the matching. I can produce a story of your demographic data change from the date of your birth into the date of today, and all the changes, or change the phone number, change address, change name. I have all the records. I can find all of them automatically. That's kind of scary thought, but I can do that. And major obstacles is overcome the complexity and the multiple dimensions. There's a minimal set of dimensions. Okay, you have a gender, you have a name, first name, address, phone number, etc. Okay, and the most difficult part is the constant changes, because all these will change, even including gender can change. In America, gender can change. You know, I'm a man turned to a woman. Someday, it has happened. All right. So what we have done is we did something called public signature hashing. So it's like compression and hashing and the signature. So what we have done, I'm going to fast forward this one. Okay. So I'm not going to worry with all the details. And I use the performance data. Okay. So this is what happened. This student 5 years ago, and this is a Daniel Levenstein edit distance speed. 5 years ago, they're making 955,000 matches takes that much time. Okay, in terms of milliseconds. Okay, now taking this much time. How much time to speed up? Accelerate to find, click to 6,000 times speed up. Now, it was complexity that was almost impossible, now becomes possible. It becomes plausible. So this is the progression of what's going on. And then we compare I don't know how many people here know tri-join and the bi-tri-join. These are the fancy data structures, the fastest matching, approximation matching data structures in the world at the moment. Okay, we are slightly slower. Okay, we're slower, but we use less memory, and we are more accurate. We don't miss anything. So that's the major results, and he's about to graduate by this fall semester, and I'm holding breath to make sure that this happens. And this research is supported in part by City of Philadelphia, and Deputy Mayor's Office of Public Health and Opportunities. So, stop for questions.
Any questions?
I have a question on the first talk.
Yes.
Yes.
I turn on the microphone. Yes.
Okay. Yeah. So I have a question on the first talk.
Oh, okay.
I'm just curious to know one thing. Given a problem, is there a way to know or measure the level of reproducibility that is possible?
Yes. The method is called timing models. If you Google search Justin Shi and scalability analysis, the paper will jump out. Yes, I'm the only guy who does this. So the paper is 1996, and I did a paper for the basic model, and there's a journal paper on the distributed parallel computing, and on the very complex model, and it's also on 2012 the supercomputing conference on 5 numerical models, so-called NAS models. But if you give me card, I'll send all the paper to you.
Sure.
Okay, it answers yes. So once we can find the equilibrium, then it can become viewable. Before the equilibrium, you cannot predict it because the timing is haywire. You cannot predict, totally unpredictable. Now you can, yes. Any other question? We have one more talk. Yeah, I think that's yours.
Okay, thanks, Professor C, for giving the good presentation. Thank you. Okay, our next presentation is data analysis with interactive visualization with R package. So Cho Wo Yi. Not here?
Not here. You say, I have one more talk, but I have not here.
No, I think no, they would give it up first.
Okay.
Not here, yeah.
So next one is agenda-less perspective of use of social
They
network.
did that already in the morning.
Oh, okay.
So this is fine.
Yes.
I can speak back.
Okay.
What's next?
This is finished. I didn't drop in.
But then we can go to
I just have the cap plus not done, so that's it.
okay, then why don't you come back and do the cap?
Want me to cap plus?
Yeah, yeah.
And you sure you have an energy? It takes some juice. Seriously. Okay? And then you have to be willing to challenge some status quo. Otherwise, it's not going to work, man. So, give me the cap plus.
Cap plus and then predicting controversy in the Senate. That's the video, right?
Now, here's my favorite talk, cap plus. Okay? Cap plus is the favorite talk because this is fresh in my head. And I didn't have to prepare for too much, but it's really complex. So this is data consistency, okay? Data consistency means that if I put an update into a server, I want this same change to cross-copy across all the machines that I made a copy, okay? And I have to have non-stop service. I think Baidu should be interested in this, okay? Non-stop. Can anyone provide non-stop service at all? Even this something that we even attempted. Okay? So what it takes to make these things happen. And again, we have to refresh your mind is that why do we have to do extreme scale research? Because only on the extreme scale is weaknesses gets exposed. Okay? Smaller scale, you don't see them because the probability is too small. So well-known process challenge. In 2000, Professor Eric Brewer from Berkeley made a conjecture, okay? In a conference, he said CAP means data consistency, service availability, and the network partition tolerance. Three of them cannot be claimed at the same time. Okay? 2002, Seth Gilbert and Nancy Lynch from MIT proved formally, okay, mathematically, the CAP is right. So therefore, CAP conjecture turn into CAP theorem. Okay? Now, to answer his own cause, and Eric Brewer proposed eventual consistency. Okay, he proposed that, and that becomes almost in every curriculum that the computer science teaches. And in 2012, an IEEE Computer magazine produced an entire issue, and at the top of the cover is CAP and 14 years later. Now, if you happen to read that magazine, and please read again after this talk, you'll find the holes in it. Okay? Another thing to remind you, in 2012, and as I said, the CCC community has a white paper produced under the title of 21st Century Computer Architecture by a group of professors from Stanford University, MIT, Berkeley, and the Caltech, and a bunch of those schools. They're claiming the inflection point has been reached. And with all that said, and what's the future of big data? You know, you can do a lot of analysis at the top, and then the bottom is going down. So what the heck are we doing here, man? Something is fundamentally wrong. Okay, the train is off the track already. So here's an example, it's a picture why consistent is a hard problem. It's really hard problem. Okay, here's something called a split brain challenge. Let's see how smart you guys are. Okay, here are two servers, copied exactly. Okay, the two users, they're updating the data at the same time. The line in between is a magic device synchronizing G1 with G2. Okay, anything that a server B, user B produces is automatically copied in here. Anything produced by user A is automatically copied over there. And the things going hunky-dory. Assuming everything is going fine, there's no update conflicts. Assuming all that is going hunky-dory, no problems. Okay, then something happened. The red line happened. Okay, red line means the link between the two, G1, G2, is broken. What do? Now you have a C and A and a B coming to talk. You want a data consistency, you have to cut service. Nobody can have a service because my server's down. It's not true. Those are up, which you can't provide service because you have no consistency. Right? You lose A. You want a C, you lose A. Okay, you want A, you lose C. And you have a network partition, you want to provide availability, you lose C as well. So the three are really like impossibility. You cannot make it happen. You know how to make it happen? Hello? It's an interesting problem, okay? So, you know, Eric wasn't really dumb because he was the founder and the CTO of a company called Inktomi. Okay, he did a lot of work on data caching for many years and made a success out of it, made a lot of money. He's a company that has millions of dollars, billions of dollars, billions of dollars right now. He didn't have to work really. Okay, the approval, however, if you read the Nancy Lynch proof, and I actually happened to have a proof in my hand and I read it, wow, there are two assumptions. Okay, now if you read into two assumptions, that you'll be surprised yourself. Okay, some of you may not even want to read that formal proof, but I'm risking my life to read it. Okay, I'm going to see it and I want to see how they prove things like this. And it's really hard to prove, right? The first assumption we call arbitrary message loss. Does that have to do with strange? It's very strange. See, why are you in a mathematical proof? Why do you assume the message can be arbitrarily lost? In a normal person's mind, nothing is lost. I never lost anything, message-wise. Have you? Have you lost messages? I don't think so. Okay? But why Nancy assumed arbitrary message loss? Why? Number one question. Number two, they assumed that replication is always synchronous. So if data copy happens, the same copy goes to all servers instantaneously. Everybody gets the exact same copy. Now, this is for obvious theoretical reasons. Without that, it's very hard to prove mathematically. Okay? Only with instant copy and you can prove mathematically. Because mathematics is not a procedural language. You cannot describe A happened and B happened. It's very hard to do that. Okay? So the first assumption goes back, my first talk. Hello? The dependencies, weak link. Okay? Because of this, because of layer 5 to 7, I was the first guy who saw this. Nancy saw that too. Okay? Nancy saw that. Okay? She put it in the paper. Okay? Formally. Now, why nobody taking care of it? Don't ask me. It's beyond my pay grade. So you're going to check yourself. Okay? The second assumption is, can synchronous replication really happen? So, if you have not worked for companies, I think Mori will have a first-hand experience. Nothing is synchronous. Serious. Okay? When I say even send a return, but the servers receive that return signal, all the servers will receive at different times. Nothing is synchronous. Forget that. Okay? But in industry, there's something else. For those who have taken computer science class, how many of you know the two-phase commit protocol? Hello? Two-phase commit protocol. We simulate, okay? Computer science says we simulate. We simulate synchronous replication. We use something called the two-phase commit protocol. You know what? Once you use that, you kill yourself. Okay? It kills performance and it kills reliability at the same time. It's really sharp knife. Kills everything. Now, how many people actually have really used synchronous replication in production? I'm pretty sure Bible never do it. Am I right? It's always asynchronous. Always, always. Because synchronous kills performance. Now, if that is true, why synchronous replication is assumed in a formal mathematical proof for capital? Ask yourself the question. Something fishy is going on. This is recorded? Hello? It is. Are you going to publish this?
Yes,
We didn't.
yeah.
Okay, refrain your enthusiasm, okay? I might get a bomb threat. But it's true, I'm not making this up, okay? I'm not making this up. Okay, the secret sauce is a two-phase commit protocol must go. The question is how to make it go, right? So how do you get rid of two physics bits? This is something that you guys will learn as computer science undergraduate. Okay? And then, so here's what you do. Okay? In industry, this is industry solution. Here's a database server. Okay? Two users come in, and there's a replication mechanism in the server, and there's an asynchronous replication going on. So this is how things go right now. Okay? So this is the replicating engine, and then they change, they copy it here. So the problem with this mechanism is you get both hits. Okay? You get hit on performance because of this. You can't go any faster than replication. There's a queue going on here, right? So what's the queuing theory says? Lambda in must be less than equal to lambda out, otherwise the queue explodes. Is that true? So you always constrain. It doesn't matter you have 8 cores, 20, 32 cores, you are no faster than the replication speed. That's number one. Number two is your back server dies, what happened to the servers? Do you dare to continue operating? I'm pretty sure Baidu will shut down. Okay? If a backup server dies and your front server is hanging out one leg, and your manager will call you and say, hey, Moody, shut down the server, man. Repair the back end. Is that right? So you can get both hit. It's stupid. It's a really bad protocol. But industry has been standardized on this for so many years, for the last 30 years, okay? And then you wonder, what happened? Yes. Okay, to get rid of it, you have to add something called replicating gateway. It's just like the conference. It's really like the name of ASC, I joined you guys. Okay? I think the ASC makes sense. It's the Academy of Science Engineering. You see that? So engineering has to be based on science. Engineering alone is not good enough. You have to have a science behind it, and engineering makes sense. So gateway liberates you from that dilemma. Okay, just like in mathematics. Okay, if you want to prove anything right, make it easy to prove, everybody can understand, what you need to do is introduce a good definition. The layer of a good definition. And then proof becomes easier. Otherwise, it's very hard. Very hard. So this is replicating gateway will do. Because the probability of an A and B failing, I mean, it's G1, G2 will fail in the equal probability, right? So there's no reason to have the replication engine on the G1. Okay, I separate it and a separate function. So put it out in here. So this is replicating function. If this guy dies, because it's a stateless, so I can replace it by anything. So it multiplies it. Okay? Same principle, just like my first talk. And this is called statistic multiplied transaction network. You see? And then I can scale indefinitely horizontally. And I also, again, I build an inductive architecture. Now this is unthinkable. You see? The impact of this is tremendous. The storage industry must rewrite the driver code. Hello? The driver code depends on virtual circuit. Hello? Something wrong with that too. Okay? If your driver code is dependent on virtual circuits, you're dead already, halfway in the grade. You have to reprogram. So how do you kill a fly in the oil? There's a fly in the oil. Okay? So I'm confessing this because it's very hard. Okay? Now here's a picture. So what if G1 and G2 suffers a temporary failure? Now here's something like a GRE test, right? So how can you recover G1 and G2 each holding like 10 terabytes of data? And I need to apply service patch. See, like 2 days ago, United States State Department suffered three-day downtime. 200,000 people's visa cannot be issued because Oracle applied a database patch on the server. Instead of fixing the instability problem, it killed the server. And Microsoft was involved as well. No comments.
It wasn't you?
No comments. 200,000 people visa cannot. Now, if you think the database industry has matured enough to handle the situation, why this happened? Why this happened? Because they have not figured out after all this time. There's a fly in the oil is that what if one of the servers needed service patches like what I'm talking about now, and they didn't have a solution. I have a 20 terabytes in my G1 and G2, and the one had a hiccup. Did not get into one update. To find that particular update will take about 2 days, maybe. Okay, so how do you do this? And repairing this takes a long time, and the solution is something called the non-stop resync. So here is an inspiration from Mobius strip. You know Mobius strip, yes? It's a piece of paper taken from beginning to end, okay? It's a half twist. Okay? This is I'm not going to ask you to read this, okay? But I can show you the proof of this. This is a picture, okay? If you apply the Mobius strip algorithm into this thing called the non-stop resynchronization, I can guarantee you 60 minutes worse downtime for any resynchronization effort, independent of size. But 60 seconds, not 60 seconds service downtime. So you can virtually have a non-stop for a whole year. We have tested the Discovery Channel, where actually we have a live customer going right now, and in Chicago. This is for real. The code is real. Okay, in production. Not open source though. Not open source. This particular not open source. And there's one sticky problem of an ACID property. Okay, and those of you who have done database research, you know there's atomicity, and you have consistency and isolation and durability, and how do you satisfy distributed transaction properties? It's really hard problem. And the solution is surprisingly simple. Okay, that was done by myself and my student in 2008. Look into that. Okay, all you need is a simple markup language and a simple discipline in the coding, like multi-threading. It's very simple. It's called RML, replication markup language. It's very simple. Now, what is exactly static multiplex transaction? Is every retransmit transaction will go to a different path, a different data set. So even the corruption is not a problem. Because if independent data set, the corruption cannot be different. The likelihood of losing data permanently is decreasing as your replication increases. Alright? So that is the fundamental theoretical underpinning of this research. And unlimited scalability is inconceivable for most of you, actually. How can this guy even talk in a podium like this? Okay, how can anybody even claim this? Unlimited scalability for data-intensive application storage. Hello? You can have any size, no upper bound, and you can have any speed you want. How can you do that? As long as you prove the inductive architecture, you have it. It's not that hard. It's really not that hard. And we did actually TPCE benchmark testing, and I showed the performance. So this is my student work, 2008, a Chinese student who did this. So you can see that as long as you remain the degree of replication equal to 2, and you increase P, and they have indefinite growth in speed, linear speed up, continuous. And then the same talk as unlimited scalability and division return. And both coexist. And the practical challenge is that I'm facing with working with the customers like Discovery Education is that all the code that right now they consider mission critical, they're not. So they have to be re-engineered. The retransmission code is not even there, so we have to rewrite all this for them. But it's only a single library, it's not that hard, but it takes time. And data storage is easiest to re-engineer, actually. Contrary to everybody believe. And mission critical data intensive applications will gain non-stop service. This time it's really non-stop service. So a company like Google and Baidu really should put interest in this. And they have the same time, and this is a summary, and I'm going to bore you with that. And this research is supported by Franklin Partnership of Pennsylvania and also Microsoft. And I used to be Microsoft partners. That's right. And also Ms. Chris Galley will pay for this trip. Thank you so much. That's some questions.